Okay, so let's do this question. This question is a bit special, and let me just read out this question. They are saying that suppose A is n cross n matrix having n linearly independent eigenvectors. Okay, so A may be symmetric matrix, may not be symmetric matrix. Basically, if it is symmetric matrix, then you know that it has linearly independent eigenvectors, right? You know this, right? If A is symmetric matrix, then we always have n linearly independent, in fact, n orthogonal eigenvectors. And orthogonal, like orthogonal eigenvectors are obviously linearly independent, but yeah, like more I mean more if I put more information, then you can say that n orthogonal eigenvectors, right? And orthogonal eigenvectors you have in case of symmetric matrix. But if it is not symmetric, then also you can have like this. That's not a problem. If it is not symmetric, then also you can have an orthogonal and linearly independent eigenvectors like this. Okay, so A, B are random matrix, and they are saying that they are having n linearly independent eigenvectors. Okay, that's good. Now, S be another matrix having eigenvectors as column vectors. I mean, S is like this. So eigenvectors, suppose there are n eigenvectors which are linearly independent. This is important because it is given to us. So n linearly independent eigenvectors, they put them as in column vectors. Now they are saying, can you just simplify this AS, which means A into S? How A into S will look like? So this is some A, this is some S, right? Which look like this. So this is S, this is A. Now, if you want to simplify this, do you remember how we have multiplied two matrices like in another way? Like one of the usual way, but some other way you remember. So what I have done, I have said like this column you can take the coefficients from this column, and then you can have the linear summation of these columns, right? And the coefficient will be coming from this column. You remember, right? So basically if this is A and this is, let's suppose, E1, E2, E3, so I can say that this product is nothing but like A E1, which is just a vector, comma A E2, I mean not comma, basically like these are the columns of this AS. So A E2, A E3, like this. So basically, I'm multiplying this A with E1, E2, E3. So I can multiply this A. I mean, like I can multiply this A with E1. Then this will be a one column. I can multiply this A with E2. This will be another column. So I can write this AS like this. I can write this AS equal to this is E1, right? So I can write this as A E1. So you can multiply this A just like this A into E1, and then A into E2, like this AEM. Okay. Is this okay to everyone? Basically, given any matrix, given two matrices, basically you can do in whatever way you want to multiply. Like you can treat this matrix as a column matrix, which means, okay, let me just treat this as a row matrix first. Let's say this is row 1, okay, row 2, like vector, like I mean I have written like this, but in fact it is just R1, R2, R3, where R1, R2, R3 are row vectors, right? And let's say this is C1, C2, C3, something like this. Okay, so these are the column vectors. So you can just say that this is C1, C2, C3. So basically I have written this matrix, these two matrices in the compact form. Okay, so R1 is one row, one entire vector, R2 is one entire vector, R3 is one entire vector, but I have written in the compact form. Similarly, I have written this C1, C2, C3 in the compact form. So now you can say this, just treat them as a scalar. Just treat them as a scalar. R1 as a scalar and C1 as a scalar. Like just for the sake of understanding, just treat them as a scalar. So R1, and you can just say that it is nothing but R1 into C1, which is a dot product, R1 into C2, R1 into C3. Just treat them as a scalar. Similarly, R2 into C1, R2 into C2, R2 into C3, like that. I mean, you can write two matrices in the compact form, like this. Anyway, like whatever way you like. Maybe if you like to write first matrix as a column matrix, another matrix as a row matrix, then also you can do it. So basically, you can say this is C1, this is C2, this is C3, right? This is R1, this is R2, this is R3, then it will be basically C1, C2, C3, right? R1, R2, R3. Now, basically, like you need to keep the dimensions correctly, but you can treat them as a scalar. So it will be C1 R1 plus C2 R2 plus C3 R3, right? Basically, you can write in the compact form. It will be C1 R1 plus C1 R2 plus C3 R3. And in fact, like the C1 R1 is one matrix, C2 R2 is another matrix, C3 R3 is another matrix. But anyway, that's okay. This is summation of three matrices. Basically, you can write two matrices multiplication in the compact form also. So, like in fact, you can write if these are the two matrices, you can say that, let's suppose this is row 1, okay, this is row 2, this is row 3. Let's suppose these. Then you can just say that, okay, let me just write this whole matrix as a compact form A. Then what it will be? It just treat them as a scalar. So it will be A into R1, A into R2, A into R3, right? But you need to keep the dimensions, like you need to take care of the dimensions. Similarly, you can you can do the compact representation of this. This is A, this is C1, this is C2, this is C3. Then you can just say these multiplication is just A into C1, okay, A into C2, A into C3. Okay. So anyway, like you can multiply matrices in the compact form also. So just treat this A as just one scalar, and you can just write A into E1, A into E2. This is a valid multiplication. There is no problem. So what is A into E1? Can anyone tell me? If E1 is eigenvector, can I just say that A into E1 is the lambda 1 E1? I can say, right? So basically, A is one matrix that was given to me. S is another matrix that they have said like S is one matrix such that S is having eigenvectors as a column vectors. That is given to me. Then they are saying just simplify this AS. Just simplify this AS. So I can say that let me just simplify this AE1, AE2, AE3 like this. Okay. Then I can say that see, this AE1 is just lambda 1 E1. This is just lambda 2 E2. Okay, this is just lambda 3 E3. Okay, like that. Now if in that case you can say that, okay, like you have almost simplified this AS, but let me do it little bit more. Okay, so AS is coming out to be like this. Is this okay to everyone? Like how we are multiplying two matrices. So you can just multiply this A with every column and you will get columns like this. Then can you also rewrite like this? This is E1, this is E2, this is E3. Can you also rewrite like this? Lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. See here, can you also rewrite like this? See, like if you multiply these two, are you getting this? Let me just quickly check. This is saying the first column will be you will be getting by lambda 1 into first column plus 0 into second column plus 0 into third column. That will be lambda 1 E1. Yes, you are getting lambda 1 E1. And similarly, you will be getting lambda 2 E2 by 0 into first column plus lambda 2 into second column plus 0 into third column. You will be getting lambda 2 into E2, right? So basically, you have simplified AS into this form. Now you are just saying that AS equal to. So actually this is a bit special. That's why I'm simplifying it again and again. AS equal to, this is just S into, let me just call this matrix as capital lambda. Okay, capital lambda. So this is AS equal to S lambda. That's how we are simplifying this, right? AS is just S lambda. Now, since the eigenvectors are linearly independent, that is given to me in the question, that eigenvectors, there are n linearly independent eigenvectors, that means S inverse exists, right? S inverse exists because these are linearly independent columns. That's why S inverse exists. Since S inverse exists, I can just multiply with the S inverse both sides, and then I will be getting this. Since S inverse exists, otherwise I can't do it. So A is finally this, where S is what? S is the eigenvectors E1, E2, E3, right? And this capital lambda is eigenvalues, lambda 1, lambda 2, lambda 3. and this S inverse is just like inverse of this eigen vector matrix, right? Is this okay? Like how I'm simplifying this A into, you are doing A into S, it will be A into S is given to me like this. Then you are doing A into E1, A into E3, A into E2, A into E3. Then you got lambda 1 E1, lambda 2 E2, lambda 2 E3. Then I'm saying that I can rewrite it like this. Then let me just take this matrix as a capital lambda, and then you are getting AS equal to S lambda. Then you will be getting A equal to S lambda. Since S inverse exists, because it is given to me that that these eigenvectors are linearly independent, that's why S inverse exists. So I can say that A equal to S lambda S inverse, right? So basically, any matrix A can be written in this form, if S inverse exists. Which means what? Which means like if you have n linearly independent eigenvectors, then only S inverse exists, right? Because S is just all the eigenvectors. S is just all the eigenvectors, yes, non-singular, right? If S inverse exists, then you can write a matrix A like this. If you have, for any matrix, if you have n linearly independent eigenvectors, then you can write that matrix in this form. That is actually called diagonalization of matrix. Diagonalization. Okay, that is called diagonalization. Anyway, like they have asked just one time in one of the option in the gate, but I just shown you that it is not very tough. Like you can just multiply A into S and you will be getting S lambda. Basically, AX equal to lambda X, that you know, right? AX equal to lambda X, that you know. And this is just one eigenvector. And instead of taking one eigenvector, can you take the set of eigenvector? Then can you say AS equal to lambda X? Here you have the capital lambda, but that's all, right? Instead of just one eigenvector, you can take all set of eigenvectors. If the all set of eigenvectors are linearly independent, then you can also multiply by the S inverse. Okay. So anyway, like any matrix which is having n linearly independent eigenvectors can be written in this form. What is the benefit of this? What is the benefit of writing this? Actually, taking power is very easy. Like if you just take, let's suppose you can write a matrix like this. Then you take, let's suppose a cube. Let me just start with a square. Taking power is very easy in this form. So you will just say a square is just this. Like 2 times multiplication of this. Then this will be identity. Then this will be just S. And this is diagonal matrix. So finding power of the diagonal matrix is very easy, right? This is a diagonal matrix and finding power of diagonal matrix is very easy. So this is lambda square S inverse. So finding power of a square, like A, is very easy. Like if you want to find the power of A100, then you can just say like this. Why? Because like if you keep on doing this, then this matrix, like A square is coming out to be like this. Similarly, A cube will come out to be like this. So finding power is very easy in that case. Extremely easy. You just need to take the power of this scalars, because diagonal matrix finding power is easy, right? So that is why. If Amar is asking if n linearly independent eigenvector exists, then we can write a completely based on its eigenvector and eigenvalue. Yes, yes. That is actually called eigenvalue decomposition. And like obviously this is not important for gate, but in machine learning there is called singular value decomposition. That is even allowed us for rectangular matrices. And these decompositions are very important for machine learning. So anyway, so in from the gate point of view, you only need to understand this, that if A is given to you, then if you are having n linearly independent eigenvectors, so can you simplify this AS? So yes, you can do it. A into S will be like this. A into S is this. So A even, so you can just simplify like this. So very easy. Should be able to do it, right? Should be able to do it. So you can write A like this. A equal to S lambda S inverse. So this is like, this should be done from gate point of view. Okay. Yes, Amar, like we can do it. There is nothing fancy here. You can just multiply this matrix with the another matrix like this, and you can just rewrite matrices. Okay.